Hello, and thank you for joining us for what should be a very interesting webinar. My name is Lindsay East. I'm the Marketing Manager for Wyatt Technology, and I will host this event. Today you will hear two presentations discussing the innovations and applications of ultra-high performance size exclusion chromatography, or UHP-SEC, and multi-angle light scattering, or MALS, for the analysis of biotherapeutic proteins. Our speakers are Dr. Stephen Koza, Principal Applications Chemist for Waters Corporation, and Dr. John Champagne, Senior Application Scientist for Wyatt Technology Corporation. Time permitting, we will conclude today's webinar with a brief question and answer session. If you have a question for either of our presenters during the webinar, please use the questions feature located on the GoToWebinar control panel on the right side of your screen. The control panel is automatically collapsed upon opening the program, so if you don't see it, please look in the upper right corner of your screen for an orange arrow button and select it. This will open your control panel where you'll be able to view the questions feature. Please type your message or question in the box and be sure to indicate which presenter you are addressing. So first we will hear from Dr. Stephen Koza, who leads a research and applied science group at Waters that has a primary focus on the use of UPLC, HPLC, LC-MS, and sample preparation techniques for the analysis of biomolecules. Prior to joining Waters, he had nearly 20 years of experience with Genetics Institute, Wyeth, and Pfizer, where he was primarily involved with biopharmaceutical characterization and analytical method development. So now I'm pleased to welcome Dr. Stephen Koza.
Thank you, Lindsay, and good afternoon or good morning, depending on where you are. The title of our presentation today is Innovations and Applications of UHP-SEC and Multi-Light Scattering MALS for the Analysis of Biotherapeutic Proteins. And the first part that I'm going to present is going to be on the SEC separation. To begin with, what I just want to talk about briefly are the principles of size exclusion chromatography, just so that we're all kind of thinking about the same things here. On the bottom of this slide is kind of a simplistic diagram of really how this separation works. What we generally have, and shown in this separation, are two molecules of different size, one about twice the size of the other, representing a monomer and a dimer of a protein. And on the surface of an SEC particle, we have pores that have kind of a structure that stylistically can be represented by what we see in the left, where we have bigger pores and smaller pores, and they're wider at the top and narrower at the bottom. I'll show you a photograph later that kind of shows you what these pores look like. Generally, as we run through a separation, the larger a particle is, the less of the pore volume it can explore, so it spends less time in the pore, more time outside of the pore, so those come out first. The smaller the particle is, the more of the pore volume it can explore, so it will come out later. The important things to remember in these separations is that it's not really based on molecular weight, but on the size of the protein or the Stokes radius. And John's going to go into a lot more detail about how those things are determined when he talks about MALS. The pore size and the pore volume of the particles that are used are really the critical parameters of the separation. These separations are isocratic. And in an ideal SEC separation, the K prime is 0 relative to the binding of the particles to the surface. So what we need is a really good method optimization in order to get a minimal amount of absorption of our particles to the surface of our analyte to the surface of the particles. And the fifth bullet point here is that really this SEC is a very low resolution technique. All of the analytes elute in either one or less column volumes. So we have a very low peak capacity. And if you compare that to other methods, such as ion exchange or reverse phase, when we run gradients, we can have analytes elute to hundreds of column volumes, so we can have a much higher peak capacities. So taking all these things into consideration, let's look a little bit at what we want to do to develop an SEC separation. The first thing to think about is, well, what are we dealing with? What are these separations being driven by? The photograph on the left is an SEM of an intact BEH-SEC particle. What we can see is it's a very small particle. These are, in this case, it's a 1.7 micron particle. It's about 1/10 the width of a human hair. And you can see that it has this porous structure on the surface of it. If we take that particle and using a broad ion beam, we cut that particle in half, we can get an image like the one on the right, where we can kind of see that this pore structure really extends deep into the particle. So during the course of our separation, our proteins are really diffusing in and out of these particles. So a few things we want to talk about when we deal with SEC method development. One of the primary things is really we want to, as we pick a column, we have to think about what LC system we're going to be running that column on. So the important considerations with the LC system are that the pressure limitation of the LC system should be compatible with the column that we choose. And also, and probably more importantly, is that the extra column dispersion of the LC system should also be compatible with the column volume of the column that we select. And this is mostly going to be driven, in this case, by the ID of the column. And what do we mean by extra column dispersion? There's a little diagram on the bottom of the slide, and what you can see is that if you start with a nominal injection volume of a sample, and you take the column out of line, and it's shown in the arrow in the center, replace it with a zero dead volume union, you'll get a peak out at the end that'll have a certain width. The width of that peak, the volume that that peak takes up, will be the dispersion volume of the system. So you can imagine that the wider that peak is that comes out with no column in place, the lower the resolution ultimately your SEC separation is going to be. And the important thing to remember in an SEC separation, since there's no binding to the surface of the column, there's no pre-concentration effect, that the dispersion that occurs in the autosampler as well as in the detector will basically have an effect on ultimately what we get for peak widths out of this separation. This is demonstrated quite nicely in this slide. In the top set of chromatograms that we can see, what we're looking at is the dispersion that happens before the column, the dispersion that happens of the peak on the column, and the post-column dispersion. The top chromatograms, we have a 4.6 millimeter ID SEC column on a UPLC low dispersion system. We can see that we start with the injection, and it gets slightly broader from a zero volume as we come out of the upper left here, and we see that the peaks are just a little bit broader, and then by the time they come out of the column, they're separated and they've dispersed a bit, but we have to deal with that because ultimately that's driving our separation. And then as those peaks get introduced into the detector, signified by the sigma post column, what we can see is that the peaks actually will lose a little bit of resolution as they disperse inside in the detector. In this case, it's a UPLC detector, so it's a low dispersion detector. In the middle set of experiments, we can see that we're running a 4.6 millimeter ID column on an HPLC system for an SEC separation, and this has greater than 30 microliters of dispersion. So when the peak comes out of the autosampler before it hits the column, it's already significantly broader than it was in the UPLC system. That peak gets further dispersed as it goes through the UPLC column. So now if we were able to look at how that peak looked on the column at this time, we'd see something as demonstrated by the chromatogram in the center where the resolution is about 1.4, and then as this peak then goes into a more dispersive UV detector, we can see that it gets dispersed even more greatly, so that we completely lose a lot of the resolution that we see in the top right chromatogram for the 4.6 millimeter ID column on a UPLC. The way to combat this, if we do have an HPLC system with high dispersion, is to actually use a larger column. If we use a larger ID column of the same length, fundamentally the resolution of an SEC separation is independent of the column ID. What we're going to wind up doing is running at a higher flow rate and a larger injection volume. So what we'll see coming out of the detector is really a peak that's very comparable in the time domain as we look at it to what we see for the peak in the upper left-hand corner for the pre-column dispersion. As that peak then goes through this wider bore column, the resolution will be equivalent to the resolution that you would see on the UPLC or 4.6 millimeter ID column on a UPLC system. And then as it disperses a little bit more in the higher dispersion detector, we'll see basically that fundamentally we'll get the same result from running an HPLC or 7.8 millimeter ID HPLC column on an HPLC system as we would on a UPLC system. So that's a pretty important concept to remember. And ultimately what it means is that if you have a low dispersion system, you can go with a lower ID column, and if you have a high dispersion system, you have to go with a higher ID column in order to get optimal performance. So this is a solid example of what we're talking about here. In the upper chromatogram, we have a UPLC 4.6 millimeter, 1.7 micron particle size column run on a UPLC system, and we get a really good resolution between the two main peaks that we see here. This is a very low dispersion system. If we take that same column under the same conditions and run it on a higher dispersion system, we can see that our resolution goes from 2.37 down to about 1.37. So the system dispersion in SEC is absolutely critical, and whether it occurs before or after the column is equally important. So if we're going to select a column, we really historically have had three choices. We have basically a cross-linked agarose column. Some of the earlier developed SEC columns were these. And the cross-linked agarose, Cefidex type GE Healthcare Science columns, they have a weakness that they have very poor mechanical strength. They can't be run at high flow rates. They're very compressible particles. But they have a significant advantage in the fact that they have very low absorption of proteins, and they can be useful for a lot of reasons because of that, despite their limitations as far as mechanical strength. Following the introduction of these types of columns, we had the introduction of silica columns. Now, silica columns have very good mechanical, or silica particles have good mechanical properties, but they have significantly higher residual Silanol activities, thus requiring significantly higher levels of ionic strength in order to minimize interactions between proteins and those residual Silanols. And in a compromise or advancement from silica, Waters a number of years ago developed the BEH particle, which is a bridged ethyl hybrid particle. It's basically a silica particle with some bridged ethyl groups inserted into the matrix of the silica. What this gives us is good mechanical properties equivalent to that of silica, but reduced Silanol activity relative to silica. So these are the three types of basic particle materials that we can select from. To demonstrate the difference between silica and BEH, this is an example where we're running lysozyme and a low ionic strength mobile phase, and we can see in the top chromatogram where lysozyme is actually coming out past the buffer peak, indicating that it's interacting with Silanol groups on the silica. And then as the column goes through about 600 lifetimes, what we can see is that the amount of diol coming off the surface and the exposure of new Silanol groups, we see a significant change in the retention behavior of this lysozyme high PI protein on the pure diol or pure silica-based column. On the bottom chromatogram, we see the same experiment done with a BEH column, where what we see is that there's still some interaction. We've intentionally made this mobile phase low ionic strength, so we do see some interaction. Lysozyme should typically come out much earlier than the 4.5 minutes we'd see here if the ionic strength was higher in this mobile phase, but it's not quite as interacting as we see for the silica. But more importantly, we can see that over the course of the lifetime of this column, we don't see this evidence of diol bleed such that we don't see a significant shift in the retention time. So silica is a lot less stable at pHs of neutral and above, whereas BEH is more of a stable particle. So pore size is an important factor. We took a look at the inside of these particles earlier, but you can see that as we go up in pore size with these SEMs, you can see that the porosity of these particles and the size of the spaces in between the solid parts just gets larger. So ultimately what that means is we're going to be able to separate larger proteins with the higher pore size and smaller proteins with the smaller pore size. And one of the ways that you can select a column that's going to be optimal for your given separation is to really look at some of the calibration curves that vendors that make these columns generate. And this is one for the UPLC BEH-SEC set of columns. And you can see that what you ultimately want to do is select a pore size where for your approximate molecular weight for the proteins that you're separating, that you're somewhere within the pseudo-linear range of the separation. So you don't want to be to the extremes where small changes in volume indicate large changes in molecular weight. You want to be somewhere where it's somewhat pseudo-linear. A way that you can extend the pseudo-linear range of your separation is shown here. And in this case, what we're looking at in the top chromatogram is a separation on the BEH 200 angstrom column of a set of molecular weight standards. And you can see that the separation of peaks 1 and 2, which is thyroglobulin and its dimer at 1.3 megadaltons versus 667 kilodaltons, it's not very good for the 200 angstrom column in the top chromatogram, but separation between peaks 3 and 4, IgG and BSA, are well resolved. In the bottom chromatogram, we can see that we get a much better separation between peaks 1 and 2, the thyroglobulin and its dimer, but not as good of a separation and not even a baseline separation between peaks 3 and 4. If we combine the 450 angstrom and the 200 angstrom column as shown in the middle chromatogram, what we do is we kind of compromise both separations. We have the same total column length of 300 millimeters, but we get adequate separation now between peaks 1 and 2 as well as 3 and 4. So if you have a sample that has a wide range of molecular weights that you need to separate, it's a consideration that you have. Another part of an SEC separation that's important is particle size. The advantage of going to small particles, as you'll see, is realistically that you can have shorter run times. Ultimately, we could scale any separation to particle size as we go to bigger particle sizes, we're going to have longer run times. If we look at the pair of chromatograms on the left, we're looking at a comparison of a 5 micron SEC separation to a 3.5 micron SEC separation on the bottom. And what we can see is that even though the pore size is slightly different, therefore we see a slight difference between the resolutions of peaks 1A and 1B, we can see that the smaller the particle size, we certainly see sharper peaks on the bottom chromatogram than we see on the top chromatogram. A more dramatic example of this is as we get to a larger pore size, the 450 angstrom shown on the chromatograms on the right, where we can see that the top chromatogram is based on an 8 micron SEC separation, and the bottom is a 3.5, almost a 50% decrease or greater than 50% decrease in particle size. And you can see that by going to the small particle size, we see a significant increase in the resolution of the peaks. And then another extreme example of that, we can see that, as I mentioned before, we can always scale these separations. So in the top chromatogram, we have our HPLC separation, and in the bottom chromatogram, we have our UPLC separation. We'll focus on the UPLC separation first. we can see that this separation is taking place on a column that's a 300 millimeter length column, and the particle size is 1.7 microns. If we want to get the same resolution that we see from this separation on a particle size that's twice as big, in this case, a 3.5 micron HPLC column, the first thing we have to make sure is that we match the length over the particle diameter ratio. That means we have to run a HPLC column that's twice the column length of our UPLC column. This will give us the same number of plates. So if we do that and then we adjust the flow for the size of the particles, you can see that in the top chromatogram we get a comparable separation to the bottom chromatogram. You'll notice, though, that the big difference between these two separations is that the bottom separation takes place in 7.5 minutes, and the top separation is almost 5 times longer at about 37 minutes. So what drives this? Why are these separations so much longer for HPLC separations than UPLC separations? And it really boils down to the Van Deemter curve, and Waters does love Van Deemter curves, and we like talking about them. So ultimately, on the upper right, we can see a classic small molecule Van Deemter curve. The main figure in this slide is an actual Van Deemter curve generated for a monoclonal antibody on 2 SEC columns. What we can see is that as the plate height decreases for our linear velocity on these 2 different columns, 1.7 micron ID particle versus a 4, that the plate height is significantly lower for the 1.7 micron. The lower the plate height is, the more plates we have per column, so the greater the resolution that we're going to have. And that's borne out by these data. And this is really driven by 2 variables in this. One is the A term of the Van Deemter, which is really driven by eddy diffusion, or the diffusion between the particles. The other part that really changes significantly as we go to smaller particles is the C term, which is the mass transfer term in and out of the particle. So you can imagine the smaller the particle is, the more rapid the analyte diffuses into and out of that particle, and that's shown by the lesser slope, that lower slope that we see for the 1.7 versus the 4. So this is basically why we see the significant advantage in going to small particles, and really what it does for us is allows us to basically have shorter analysis times. So as we're developing our method, one thing we can do to always get, regardless of whether we have a UPLC or an HPLC-SEC method, we can always add more column length to get more resolution. Now you remember that, chromatographically, the resolution improvement will be to the square root of n, or the square root of the inverse, or the square root of the increase in the number of plates that we have. So shown in the top chromatogram, we have a separation on a 150 millimeter length column with a resolution of 2.1, and on the bottom chromatogram, we have a 300 millimeter column with a resolution of 2.8, which is about a square root of 2 increase in the resolution that we see. Another thing we can always do to tweak our resolution in SEC is to decrease the flow rate or increase the flow rate. As we go to a lower flow rate in SEC, we'll get greater resolution, and that's shown in this slide. The top chromatogram is at 0.2 mils a minute. We have a resolution of 2.5 or 2.4, and then going all the way down to the bottom chromatogram at 0.8 mils a minute, we have a resolution of 1.3. So you can dial in a resolution that gives you the flow rate that gives you the resolution that you need. The compromise here is that as we go to lower flow rates, obviously the run times, the analysis times are going to increase. I'm often asked, well, if I can increase my resolution by decreasing flow rate or increase column length, which is the better choice? This slide summarizes that decision. What we can see in the top chromatogram is that we've taken a 300 millimeter column and we run it at 0.5 mils a minute, and we get the separation shown above. In the bottom chromatogram, we wanted more resolution. So what we've done is we've taken now 2 columns in series. So we now have 600 millimeters of column length, so twice the column length is above, but we've doubled the flow rate, so we have the same run time. So you can see, demonstrated by these data, that all things being equal, if you want to have lower analysis times but increased resolution, it's always a more efficient way to get that is to add column length as opposed to decreasing flow rate. The final thing that we need to think about in terms of just running our separation is really the sample load on the column. So this really relates to injection volume. You can see that on the chromatograms on the left, that as you go to higher and higher injection volumes in SEC, you can lose resolution, especially as those injection volumes really exceed the capacity of the volume of the column. Ultimately, what we can see on the right is that as we go into a higher and higher concentration for our sample, which in this case doesn't mean concentrated this sample as much as it means diluting it less if possible, we can see that by just going to higher concentrations, we really have very little effect on the resolution that we see. So if we really need to increase the sensitivity to see low abundant species, it's always better to increase the concentration as opposed to decreasing or as opposed to increasing the injection volume. So one thing we want to think about is optimizing our system so that our mobile phase is optimal and we get a good peak shape and recovery. That's shown in this experiment with AutoBlend Plus, where we looked at a series of pHs and salt concentrations. And what we can see is that as we're at higher salt concentrations and lower pHs for this particular separation, we get a nice consistent profile with good recovery of our high molecular weight species. So this is a good area to operate in this upper right quadrant of this design space. In the lower left quadrant, we can see that we start losing resolution and losing recovery of our high molecular weight species. So that would not be an optimal place to operate. We can add organic modifiers to decrease interactions with our stationary phase and our systems. And there's a lot of examples of this, particularly if we're seeing some hydrophobic interactions. So we can add either propanol or acetonitrile. And the important thing to remember is that proteins are big. They have large spaces where they have hydrophobic patches and ionic patches, so we have to kind of deal with those individually. Arginine is another molecule that has been shown to be useful in decreasing interactions of proteins with surfaces. It can improve recovery and peak shape, and there's a reference for the use of arginine for SEC on the bottom of the slide. Can also inhibit protein self-association. Want to be careful using too much arginine, as it can disrupt aggregates if it's used in too much of an abundance. It is a bit of a denaturant. We can also use alternative salts that basically we reduce hydrophobic interaction, as shown in this slide based on the Hofmeister series. Perchlorate is particularly good as an anionic salt at reducing hydrophobic interactions, as well as lithium versus sodium. Want to avoid using any of the divalent salts shown here like magnesium and calcium, since they're not really soluble with phosphate buffers. So finally, just want to touch briefly on understanding your method and characterizing your method. And John's going to talk about MALS. I'm going to briefly introduce some SEC work, but ultimately I'm also going to talk a little bit about method-generated artifacts and aggregation on the column. We can see that ultimately in an SEC system, we can actually run in a buffer that's compatible with mass spectrometry, shown here in the conversion between a PBS separation to 100 millimolar ammonium formate separation of a monoclonal antibody. And what we really want to do is get IDs for peaks 2 and 3, which are these clip forms. And we can see that based on this LCMS of the native monoclonal antibody, that the peak 2, this clip shown here, is predominantly the 2/3 molecule, so it's missing one of its Fab arms, whereas peak 3 is a mixture of the Fab and the FC portions of the monoclonal antibody. In order to evaluate whether or not we're seeing aggregation on the column, there's a couple tricks that we can do. Shown in this experiment, what we've done is taken our monoclonal antibody and concentrated it, run it on SEC, collected, and shown in the blue traces, our original run, collected the heart cut of the monomer, and then immediately re-injected that back onto our SEC system and monitored at a more sensitive wavelength, which is 220. And what we can see is that we don't see any appreciable development of high molecular weight when we do this experiment, demonstrating that our method is not generating high molecular weight on the column. Another way to approach this is to increase the residence time on the column. Shown on the bottom chromatogram is our SEC separation at 0.6 mils a minute on a 150 millimeter length column, 0.3 on a 300, and 0.2 on a 450. So in each of these cases, we get the same back pressure on the column, but the sample stays on the column longer. So if there are aggregates occurring on the column, there would be more opportunity for that to happen. And what we see is that the amount of high molecular weight is constant throughout. And for a final couple slides, just as a reminder, in order to have successful SEC in your laboratory, there's a couple things we want to think about. One is as I talked about, extra column dispersion. And in SEC, it's really important to consider the extra column dispersion that's occurring in the autosampler, as well as the tubing and connections that are used to connect the autosampler to the inlet of the column. And then, like any other HPLC or UPLC separation, the dispersion that occurs in the detector, as well as that tubing that connects the column outlet, is also critically important. The thing I want to highlight here is that what happens before the column in SEC is really critically important versus other methods like C18 reverse phase. The other important thing is we want to control microbiological contamination in SEC, such as bacteria, mold, and other things. And what we can typically see is a disruption of the flow path so that we can start seeing peak splitting when we get bacterial growth in our columns. So it'll cause the flow to go in different directions, and the chromatography will not look good. So we want to make sure that we control our bacterial growth. So I won't cover the summary. I'm running a little bit late with the slow start, and I'm going to hand it over to John. Thank you.
Great. Thank you so much, Dr. Koza. Our next presenter is Dr. John Champagne from Wyatt Technology. John is a senior application scientist and regional manager responsible for customer support across the Northeast and the Wyatt Applications Lab outside of Boston. Since joining Wyatt in 2002, John has provided a range of analytical support with expertise in the area of biochemistry and biophysics. Prior to joining Wyatt, John had several years of industry experience with Genetics Institute and Wyeth Biopharma and was primarily involved with biopharmaceutical characterization. Now it's my pleasure to welcome Dr. John Champagne.
Thank you, Lindsay, and thank you, Steve, for your nice talk discussing some of the challenges with the separation component. This is the second half of the webinar, which is going to talk about, okay, once we've done all that hard work for the characterization, or for the separation, how do we characterize it? And so the title is Innovation and Application of µSEC-MALS. The one thing I wanted to quickly talk about is, even though we're going to focus on the SEC component of separation, this characterization involving light scattering is really applicable to all ranges of chromatography. So Steve focused on some reverse phase, ion exchange, these sort of things. So the MALS system can be run as a detector downstream. The other thing I want to talk about is the importance of this detection downstream of the chromatography. Steve mentioned a little bit about the potential for column interactions as well as the challenges of column calibration. And this really addresses that, so we can get full characterization, first principle downstream of any type of chromatography and without the challenges inherent to column calibration. So the first thing I want to talk about is, what can light scattering measure? I was told that a lot of folks who are going to be listening in may not be light scattering experts, believe it or not. So we wanted to focus a little bit on some of the fundamentals of light scattering. What can it measure? So for a solute in solution, light scattering can determine a couple of things. Molar mass, typically denoted as an M sub W. In this case, it's just an M. We can also measure, in a lot of cases, the size, and we refer to that as the root mean square radius, or the R sub G. because we can measure mass first principle, we can also derive thermodynamic parameters such as the second virial coefficient to look at non-ideality in solution. And then if you transition slightly to a technique that can look at light scattering over a longer period of time, such as dynamic light scattering, same fundamental Rayleigh scattering principles as static light scattering, we just observe scattering over a longer period of time, and we can derive the translational diffusion coefficient, which can ultimately be used to calculate hydrodynamic radius. So dynamic light scattering is that sister technique to static light scattering, and I'll show you how we can employ that in an online sense. First, how does light scatter? So we teach this time and time again at our Light Scattering University, and I'll just give you a couple of slides based on the Light Scattering University course. So light scattering is an energy transfer event. So light comes in, and we can see that molecules, even if they're not a dipole, inherently, the light scattering interaction, this oscillational transfer of energy in this interaction, causes molecules to induce a dipole. And as the dipole is induced, molecules will then start to radiate their own light as energy is transferred to the molecule. And the resistance for a molecule to become a dipole and to transfer energy in a vacuum is known as polarizability. In solution, it's known as refractive index. So you can start to now see how refractive index plays a large role in the overall light scattering. But fundamentally, this is how the transfer of energy occurs. How do we utilize that transfer of energy? Well, you can see in these two cases, the case 1 here and case 2, they're both the same concentration. If we look at the fundamental light scattering equation, where the intensity of scattered light here is proportional to two variables, mass and concentration, the dNdC is the change in the refractive index with respect to concentration, but in both cases the concentration is the same. Therefore, this term falls out and this term falls out. If we look at the first case, we have an incoherent transfer of energy. So these two particles are independent. They can transfer energy sometimes in an additive sense, sometimes in a completely subtractive sense. So over time, the scattering intensity of this system is going to equate to 1. Sometimes it's 2, sometimes it's 0. In this case, these two particles are now combined in some sort of a bonding event. So they're going to always transfer energy the same, and in this case, the scattering intensity will be equal to 2. So if we look back at our fundamental equation, the intensity of scattered is proportional to the mass. As the concentration, again, is the same, this mass would be a single scattering, i.e. a monomer. This mass would be a double scattering, i.e. a dimer. The angular dependence comes about when those particles, those point scatterers, actually start to either separate, so the conformation changes, or you have larger particles which are now treated mathematically as just consisting of more point scatterers. And what will happen is, as particles deviate from one another in their position relative to the wavelength, and we look at a point of observation that deviates from the 0 angle, you can start to see now the crests and the troughs of these waves no longer overlay. At the 0 angle, though, they do. So that's why it's very critical for static light scattering to get the scattering at the 0 angle, so we know how much energy has been transferred to our molecule. And if we see the effects of the subtraction of each of those multiple components in solution, it's here in this plot where we see the relative intensity as a function of the angular position. At the 0 angle, it's 100% transfer. As the angle increases, we see a drop. Okay? The drop is indicative of this equation, this component in the equation p theta. It's the slope of that line. And that's what would have to be entered in if you had a single angle light scattering system. Single angle static light scattering is not a first principle technique. You would need to account for things like change in the conformation of these point scatterers, as well as change in the mass of those point scatterers. And you can see that reflective in the slope. So p theta would have to be corrected for if you just used a single angle static light scattering. If you use a multi-angle, not only do you not have to correct for p theta, but you can calculate it because it's the slope of that scattering intensity as a function of the angular position. And that's how we can derive the radius of particles. As far as a standard light scattering experiment, we have our laser here in the end position. We use a polarized light source, and all light that transfers to our particles, they transfers in a sense which is perpendicular to the plane of polarization, so it comes out in just a two-dimensional horizontal plane, and we can arrange our detectors around in this two-dimensional horizontal plane, and we can capture the light scattering. And whether the particles are moving downstream of chromatography or if they're not moving, simply inject it in as a plug, we can still monitor the amount of energy that's transferred as well as the scattering pattern because we position detectors in that two-dimensional plane. We use the Rayleigh scattering ratio, so we look at the ratio of the scattering intensity, initial scattering intensity versus the final scattering intensity at the zero angle. And as I mentioned to you, of course, we do so in a multi-angle approach with our instrument. This gives us a correction factor for the scattering at zero angle, as well as the pattern of scattering to determine information about particle shapes as we are eluting off, again, either a column for separation or if you just inject the sample in as a plug. So why would we want to use this ultra-high performance size exclusion? Well, for obvious reasons, as Steve pointed out. It will really give us faster resolution, faster results, greater resolution, very, very high detector sensitivity, small sample quantity, less solvent usage for a lot of cases. Again, our instruments can be run downstream of not only size exclusion, but any of the chromatography. So you may run into systems where you have aqueous, you may run into systems where you have organic. So the solvent usage, having lower amount of solvent usage is pretty critical. And certainly better productivity. As Steve pointed out, the run times are so much shorter, you can do a lot of manipulations with the chromatography and then rerun it. And so you have a lot more time to do method development, certainly increasing your productivity. Why would you want to employ MALS for this? Well, as we talked earlier, as Steve pointed out, some of the potential for column interactions, and that would lead, of course, to challenges in column calibration. And, of course, over the range of the masses that you might encounter, column calibrations, as Steve talked about, that quasi-linear component of the column calibration can be a bit of a challenge. So having first principle characterization downstream is pretty important. So measuring the mass in solution without assumptions about the polymer shape, protein shape, or chromatography properties. We can detect and characterize and quantify the aggregations, both mass action aggregations and non-mass action aggregation as they elute from the columns. Certainly identification of new peaks. We've come into many instances where we've seen peaks that were not there before. We couldn't see them before because of the dilution effect of standard chromatography. Assessing heterogeneity of the SEC peak. Using MALS, this gets back into the method development that Steve was discussing. So you have these nice peak shapes. Does it mean that your samples are homogeneous across the peak shape? MALS will give you that information. Characterize things like protein conjugates and copolymers. Reveal conformation by using online DLS, and of course the multi-angle light scattering. So anything that you could or you were familiar with traditional MALS and chromatography, we can do exactly the same thing with the UHP chromatography. So challenges when using MALS for this type of separation. So here's an example where we look at two peaks. We have a red peak and we have our blue peak. And if we start to look at how these peaks were generated, the first peak is with the UHP-SEC method, and the volumes of those peaks are about 40 microliters. The second peak is with standard SEC with an HPLC. The volumes are 440 microliters. So we talk about the volumes and how they relate to the detector volume. Here we can see the detector volume of a standard MALS systems. Standard MALS flow cell is not large. It's about 63 microliters with all the associated tubing, but it's large with respect to the peak that you've generated with the UHP-SEC, which is 40 microliters. So you can see it's not really optimal to have a a detector volume of 63 microliters. With standard SEC, it worked just fine. When you look at the broadening as a result of the subsequent detectors, as Steve mentioned, here we can see the elution from a UHP-SEC separation. So we've worked very hard to get sharp peaks. We can see the green here is the UV detection. The MALS is then followed here in red. and these are all subsequent to one another. So first detection system would be the UV detector, then it would be MALS. Finally, you can see the broadening as a result of going through excuse me, the last detector, which is the differential RI. And if you wanted to characterize things like the small fragment peaks that come up, you would completely lose that ability if you were using standard volume detectors downstream. So a new MALS for UPLC is the MicroDAWN. So it employs a multi-angle approach. This is based on our MiniDAWN Traos platform. So the angles are analogous to the MiniDAWN, so 45, 90, and 135, which is the minimum number of angles you would need to employ a light scattering technique. And this will generate the mass and the radius, the R sub G radius as I discussed. Laser wavelength of 650 milliwatt at our standard wavelength of 658 nanometers. We can look at the mass range from a few hundred Daltons up to 10 to the 7th Daltons for proteins, 10 to the 6th Daltons for linear polymers. We can look at the range is based on the angular dependence that I discussed before as far as the R sub G. So 10 is the smallest on the low end. As molecules are lower than 10 nanometers, they start to lose that angular dependence fingerprint that you would get. And so the low angle would be 10 nanometers, sorry, the low limit would be 10 nanometers up to 50 nanometers. And if you use shape-specific models, you can actually get up further to 150 nanometers. And the software will allow you to use shape-specific models, of course. If you want to employ the QELS module to expand the range for the radius, the QELS module will get you the hydrodynamic radius all the way down to 0.5 nanometers and all the way up to 30 nanometers. And of course, as with all of our light scattering systems, we have a number of detectors other than the detectors that we use for specific characterization. In the case of this one, we have a forward monitor to correct for absorbing samples. Our cell volume is much smaller, 6 microliters. And communications in this case is all digital communication, so TCP/IP protocol. And you can see here, this is the embedded COMET module, will allow for ultrasonic cleaning in case you did have those issues Steve was discussing as far as contamination effects. The COMET will work really well in that regard. So some of the features, again, moving forward, we've had to rethink light scattering, the way we perform light scattering, to bring the volumes down much smaller. And in this case, we can see we've changed the silicon pin photodiodes that we generally would use. In these cases, we use high gain detectors. We changed the read head design. Here's our COMET for the ultrasonic cleaning, the detector for the DLS fiber port. So we use an avalanche photodiode as opposed to our silicon pin photodiodes for static light scattering. And we can see the optic bench has been improved for this system to give much better stability. Our flow cell volume, we have an 8 times reduction in volume to help with that broadening as a result of running downstream of the UHP system. And we've also improved our laser module to give us a tighter focus and a cleaner beam when we're talking about lower volumes. Here's our embedded QELS module, so it's an option you can add, and that will give you, again, enhanced range for the radius information. And here you can see the radius will go down all the way down to 0.5, so it will cover really a complete range for radius measurements, whether you're talking about very small proteins, polymers, and it will go up to very large particles for characterization. So why MicroDAWN and the UT-REX? So we're getting back to some of these familiar data that Steve was talking about as far as the column widths. So this is a UHP-LC column that we utilized, and you can see the volumes here at the full width at the half maximum, so to give some indication as to the broadening as a result. So with the UV trace, the full width at the half maximum is 44 microliters, so it's maintained the separation. This is the first indication of the sharpness of the peak. If we were to look at a standard MALS detection subsequent to the UV, the broadening is not terrible, but you can see it's 55 microliters, whereas the MicroDAWN, we're looking at the full width at the half maximum, much improved, 45 microliters. And then certainly once we get to the third trace, which is differential RI, the standard differential refractive index is about 105 microliters versus the UT-REX, which is 48 microliters. So we need generally the UT-REX or the differential RI to give us that universal concentration detection, as well as in many cases the UV detector. So it's pretty important to make sure that you have a differential RI that has those small volumes that can match the small volumes from both the UV and the MALS detection, and that's our UT-REX detector. So again, let's talk about why would they be needed. Again, we've worked very hard to get good resolution, and then you can see with a standard MALS and a standard differential RI, we're looking at an example here of an IgG with a fragmented component. And you can see the resolution. Of course, we don't get baseline resolution, and it doesn't look like it's very homogeneous across the peaks, and that's probably due to the peak bleeding and the lack of resolution because of the broadening effects. Whereas if we look at the lack of broadening that we would get now with the microDAWN and the UT-REX, we can see we've maintained the integrity that was initially built in with the UHPLC system. And you can see now the peaks are much better representative as to the homogeneity of the sample downstream. And if we overlay that, you can see the obvious differences. One of the things I want to, again, talk about is that this will enable all key MALS applications on the UHPLC. So band broadening, conjugate analysis, everything that we can do with our standard chromatography analysis, we can do with the UHPLC and the microDAWN. So here's the experimental conditions, a very familiar site, the acuity systems upstream of our microDAWN and our Optilab UT-REX, as well as a UV detector from Waters. And a couple of examples. Here's a question of why are these proteins eluting so differently? Are they really MAB monomers? And we've overlaid the chromatograms here in all multiple colors, as well as the mass distributions as a function of the volume. And we can see that minimal volume that Steve was talking about that UPLC affords us. And the microDAWN revealed that all 4 MABs are indeed monomeric. And in fact, we can even see with this pink trace that we get a lot of tailing as a result. Is that due to overloading, or is it due to mass distributions? And here you can see some indication of the fact that some of this tailing may be indicative of the fact that the sample is not completely homogeneous. So it may be a combination of overloading, but if we were to extend the mass determination, it may be a fact that the masses are actually changing throughout this separation. But getting back to the original questions, are these proteins really monomers? We can now look at dynamic light scattering to give us that hydrodynamic characteristic. As Steve pointed out, separation with size exclusion is not based on mass. It's based on the hydrodynamic characteristics of our components. And the elution could be due to different shapes. So we check with our online DLS. And again, the hydrodynamic radius can be measured down to 0.5 nanometers for these samples. And if we look at the results of the hydrodynamic characterization, we can see that they are about the same. So likely, the change in the peak position is due to column interaction. We talk about some of the newer peaks as a result of this improved resolution. Here are some IgG fragments which were identified. Here you can see fragment 3 and fragment 4. We used UV detection because of the enhanced sensitivity of UV. And we can see that the calculation done by Astra software shows that these masses are about 39 kilodaltons and 24 kilodaltons for these fragmented materials. Again, talking about the flexibility of the platform and of Astra software, if we want to use, in this case, using both UV and refractive index, we can do our conjugate analysis, and this is a glycoprotein. And so the interesting thing that this will give you is not only a corrected mass for the complex, but it gives you also the mass for the protein, and then in this case the mass for the modifier, which was the glycan. So you can see if changes in peak shapes, are they due to the protein component or to the modifier component. And this conjugate analysis can be used, in this case it's a glycan, but it can be used just as readily for things like pegylation, or if you're looking at a membrane protein, so you have some membrane component that's associated with the protein, or even protein-protein interactions. So this conjugate analysis will give you a lot of flexibility using, again, both the UV and the refractive index trace. Finally, we're going to talk about characterizing fractions from preparative HPLC. And as we know from size exclusion, larger components elute first, followed by the smaller components. And if we look at just one peak, we always assume that the components that elute off of this peak are relatively similar in their distribution. And if we were to take each of these fractionated components from the leading to the apex to the tailing edge of the peak, and we were to overlay them, you can see the leading edge of the peak certainly contains more of that higher mass material. So in this case it would be the mass action aggregation of the monomer, what we're calling dimer, we're calling trimer, and then some other material. If we go to the apex, we start to minimize that effect, and certainly the tailing edge of the peak, we minimize the effects of the higher molecular weight material that has eluted. So the microdon and the UT-REX for UHP-SEC separation, both of the systems, both the microdon and the UT-REX, will preserve the speed and resolution that you've worked so hard for with that upstream UHP-SEC. The MALS and the DLS measurement will allow you to do multiple things, from mass to radius, and then using DLS, the hydrodynamic characteristics for extinction coefficients and ultimately for conformation. Very high speed, as we've been pointing out, rich information, and really open new applications for process monitoring and really a range of other areas. It's the USEC-MALS system, so the µSEC-MALS. And that's all I've got. If you have any questions, I apologize we went a little bit over, but we can take your questions now from both Steve and myself.
Great. Thank you so much, Dr. Champagne. And now we'll have time for a couple questions here. Okay, first question, I think this was for Dr. Koza. How significant is the interaction of the metal casing of the column with proteins?
That's a good question. In general, for most SEC separations, the ionic strengths are going to be high enough that those interactions shouldn't really be a concern. There will be, however, potentially some proteins, and I've actually dealt with one in the past, in one of my past lives, that no matter what we did, whatever conditions we could find, we actually ran into a problem where it would interact with the stainless steel, and we wound up having to use a peak-based HPLC-SEC column for that separation. But in general, it should not interact given the standard conditions that we separate under.
Okay, thank you. And then this, I think, was for Dr. Champagne. For a globular protein mass greater than 300 kilodaltons, what additional information comes from MALS versus a single intensity measurement at 90 degrees?
Right. So it's a good question. And again, we talked about the differences between an instrument that only uses 90 degrees and tries to get that scattering intensity at that zero angle. So for your 300 kilodalton globular component, how, and that for the most part would scatter isotropic in nature, which is to say it would behave as a single point scatter. Although very quickly, if there were changes in conditions, Steve talked about modifying run conditions. If that changed the shape or the character of these particles, they would now start to unfold, and they would change their peak position, their elution position, and you wouldn't know that. So you would still monitor them as not knowing any better with a 90-degree detector. They would still be modeled as a particle that would behave as an isotropic scatterer. But very quickly, as they unfold, they can behave as an anisotropic scatterer, which is to say consisting of more than one point scatterer. And that's where that p theta correction would come into play. So you'd have to model the shape dependency of the particle to correct for the slope that would now occur. So for something like a 300 kilodalton particle, if it was just globular, you would be able to identify that with multi-angle light scattering because your angular dependence would be 0. But the minute it started to change its position or you saw association, you can very quickly get into the range where a particle will start to become less than globular, Or what happens throughout the course of a peak separation, the peak starts to change position. Some of that component could be less than globular, and you'd be able to identify that using a multi-angle light scattering approach that would show that angular dependence. So if you really wanted to get a system that was very comprehensive and you didn't have to worry about the shape dependency on the scattering, the multi-angle system would really be your best bet.
Okay, thank you. And then I think this is for Steve. Is it important to use a biocompatible or bioinert LC system for SEC analysis?
I think that kind of relates a little bit to the first question. In general, I would say it is not that critical, certainly not as critical as it is for such separations as ion exchange, where corrosion from a system could affect the separation or the surface of the column itself. So in general, there's no real consideration that needs to be made for that.
I just want to touch on that too a bit, Steve, if you don't mind, Lindsay.
Mm-hmm.
Downstream detection, we've had a lot of questions in the past that came up is, do we have to have biocompatible systems to run upstream of our detection? And the answer, as Steve pointed out, is really no. And we're really going to be at the mercy of the chromatography component. So if it improves chromatography, then great, but you don't have to worry about the detection system downstream. There's not a lot of leaching that occurs, and if there is of any of those metal components, it doesn't interfere with the light scattering appreciably.
Okay, great. I think we have time for one more. What is the smallest difference in molecular weight that can be separated by SEC?
That's a pretty good question. Rule of thumb is in a standard SEC separation with standard HPLC type size particles, you more or less need about a 2-fold change in molecular weight, so monomer, dimer, in order to theoretically achieve a baseline separation. That can be changed by adding more plates, by going to smaller particles, longer column lengths. But that would be the general rule of thumb for a standard like 5-micron particle and a 30-centimeter separation.
And then maybe I can detect, or I can address the downstream detection about changes in the mass. It's based on the precision of the instrument. So the precision of our light scattering systems are anywhere from 1 to 3% precision based on the square root of the number of detectors. So we can detect as small as a 1 to 3% change in mass for particles downstream of the chromatography.
All right. Well, we're just out of time, so we'll conclude the webinar for today. Thank you everyone for submitting the questions, and even though we haven't gotten to answer all of them, we will compile a written response with the questions and answers, regardless of if they're read aloud. We will send each of you a link to the archived webinar of this version of this webinar and the question and answer document to view on the Wyatt website. Wyatt's on-demand webinar library is also a great resource where you can find recordings covering many additional aspects of light scattering technology and applications. If you have further questions, please get in touch with me at the contact information in your webinar confirmation email. Thank you again, everyone, for joining us, and a big thank you to Dr. Koza and Dr. Champagne for your presentations. This now concludes our webinar for today.